Hello everyone, my name is Dobaria Niketan and here we are discussing basic electrical engineering, specifically second chapter AC circuits. In our previous video, we had started various AC circuit in which we had started our first AC circuit and that was purely resistive circuit. So in this video, we are going to start our next circuit and that is purely inductive circuit. So what is purely inductive circuit? Here we had consider a pure inductor over here, or you can say only inductor, and value of that inductor is considered over here by this term L, and that pure inductor is connected across a AC voltage source having a value is equal to Vt is equal to Vm sine omega t. And when this AC source is connected with this pure inductor, an AC current is producing over here and value of that AC current for this given circuit is considered as a IT. And here what supply voltage we had provided to this purely inductive circuit, that is mentioned by this given term Vt is equal to Vm sine omega t, where Vt is nothing but a instantaneous values of that given supply voltage. Now we know that when we provide AC alternating, that is nothing but a variable supply. When we provide alternating voltage to a inductor, when AC, and because of that, when AC current will be provided to this inductor, that will produce variable magnetic flux. And we had discussed Faraday's law in our previous lecture. Basically, that was the first lecture of this AC circuit, and we had discussed that when we provide a variable flux to any conductor or coil, it produces EMF in it. So here, when we are providing alternating current to this inductor, and that alternating current, that is nothing but a variable current, its value is changing with respect to time. So when we are providing this alternating current, means we are providing variable current to that inductor, and because of that variable magnetic flux is producing around this coil or this inductor, and that variable flux which is linking with itself with that same inductor, that will produce voltage in it, that means that will induce EMF in that same inductor, and that induced EMF is also known as a back EMF. Why back EMF? Because the direction of that induced EMF which is producing in inductor is going to be opposite with compared to supply voltage, which will oppose the supply voltage. That's why that is known as a back EMF. And here we will define that back EMF by this term EB, and we can find out its value by this given term minus L di by dt, where di by dt is representing the rate of change of supply current to that inductor. Here L, which is inductance of this given inductor. And as mentioned in our previous statement, supply voltage and this back EMF both are going to be in opposite direction with compared to each other, and that's why we can write it down as a VT supply voltage is equal to minus EB, because both are in opposite direction with compared to each other. Now by considering these things over here what we are going to derive, first of all we will derive the supply current for this purely inductive circuit, and after that we will have a supply voltage and supply current for this given circuit, and based on that we will plot its waveform as well as its phasor diagram, and lastly we will calculate instantaneous power and average power for this purely inductive circuit. So let's start with the derivation of supply current for this purely inductive circuit. So by considering this equation, Vt is equal to minus Eb. If we put the value of Eb, which is over here, into this given equation, so now we have equation Vt is equal to minus into in bracket minus L di by dt. So minus and minus is going to be cancel out each other. That's why we will have a Vt is equal to L di by dt. From this given equation, we are going to derive the value of current. But here current is in derivative form, means in di by dt form. So if you want to derive the value of current, you have to remove this d item, and for that you can use the integration. So to integrate this equation, first of all we will separate the d item, and next we will integrate this term to derive the value of current. And for that, first of all, let's put the value of this supply voltage Vt, and which is nothing but a Vm sine omega t. So we had put this value Vt is equal to Vm sine omega t is equal to L di by dt. Now let's separate the terms. We are separating di and we are making this subject di. So if you make this term di as a subject, so that is equal to, here we have Vm sine omega t term, and this raised term will be going to in opposite side. So dt will be in multiplication with this term. So Vm sine omega t into dt, and this L will be in division of this term. So here we have a in division. This is the L over here. Vm sine omega t dt by L. Now this was the dt up to now. Now if you want to derive current I, so for that we need to integrate this term. So if we put integration over here, so this term will provide the I, and for that derive the value of this I, we need to integrate on right hand side also. And here on the right hand side, this Vm and this L, which is in division, both are constants. So you can take as a take them common. So we have Vm by L as a constant, and integration of sine omega t with respect to dt. First of all, remember that up to now, whatever integration was done for various reasons, that were with respect to d theta d omega t term. Now this given integration, that is with respect to dt. So that is the difference over here. Now let's start the integration. So integration of di, that is I, and here Vm by L, that is constant. So integration of sine omega t, that is nothing but a minus cos. So minus cos omega t, but here this is with respect to dt. So and here in angle we have omega t term. So this omega, which is a coefficient of t, that is going to be in division over here. So basically now we have equation, and that is first this minus common over here. So if we take this minus common over here, that will provide minus Vm by this in division we have omega into L. So omega by L, and here we have a term cos omega t. So that is over here cos omega t. So finally we have a minus Vm by omega L and cos omega t. Now again we can convert this cos theta into minus sine omega t, means minus sine theta minus 90 degree. So here in place of minus cos theta, you can convert it sine theta minus 90, which was done over here. So this was replaced by sine omega t minus 90, and this term Vm by omega L, that is replaced by Im over here. Again, what is Im over here? That is nothing but a Vm by omega L. And actually, what is omega L? That is nothing but a resistive portion of inductor, which is offered by inductor. Omega L, that is nothing but an inductive reactance. We had discussed that term in our 11-12 physics. XL, that is inductive reactance, and value of that inductive reactance XL, that is nothing but omega L. So this is the same term. So you can replace this term by XL, and Vm by XL will provide Im. So basically this is the supply current for this inductive circuit. Now based on this given term, if we plot the waveform for this purely inductive circuit, for that supply voltage is same as it was in previous circuit, and that is Vt is equal to Vm sine omega t. So in Vm sine omega t, phase angle of voltage is 0. That's why this voltage is starting from 0. And if we observe the equation of current, that is it is equal to Im sine omega t. Here in this given equation, after omega t term, we have a minus 90 degree term. First of all, minus 90 degree, that is indicating lagging term. And again, as this is minus 90 degree lagging term, so that is going to be start after 0. After 0 means here on this x-axis we are defining angle, so this is 0 angle or reference angle, and with compared to that, if we define after, that means on this positive x-axis in this direction, and this is going to be over here minus 90 degree. So waveform of current means positive cycle of current will start from this minus 90 degree, and that's why here if you observe the waveform, the positive cycle of this current, which is in dark red color, is starting at minus 90 degree. So these are the waveform of voltage and current for purely inductive circuit. Similar way, if you plot the phasor diagram, so angle of voltage, that is over here Vm sine omega t, and after omega t that is 0. So angle of voltage, that is 0, and magnitude, that is given by Vm. So based on that you can consider its length over here on angle 0, means on positive x-axis. Similar way, if we find out the vector for current, value of that current is defined by this Im. According to that value Im, you can find out certain length, and angle of this given current is minus 90 degree. When we consider xy plot, we define minus angle on clockwise direction on fourth quadrant. So minus 90 degree is going to be on negative y-axis. So here we are going to plot current I on negative y-axis with compared to this voltage which is on 0. So basically current of this purely inductive circuit is 90 degree lagging, or you can say 90 degree behind with compared to supply voltage. In reverse, or in other way, you can say that with compared to current, if we consider current as a reference, voltage is in leading condition is at a plus 90 degree at a plus 90 leading angle. So this was the phasor diagram and waveform for purely inductive circuit. Now let's derive the instantaneous power. And again, what is instantaneous power? That is the same thing, multiplication of instantaneous voltage and instantaneous current. So let's find it out. And for that, instantaneous power is equal to multiplication of instantaneous voltage and instantaneous current, and value for this purely inductive circuit V and I, that is Vm sine omega t, and for current that is Im sine omega t minus 90 degree. Now again, this sine omega t minus 90 degree, that was derived from minus cos theta. So if we put the same value again, so here we have a minus Im cos omega t instead of this value of current, and if we take this minus as a common, and here now we have a term sin theta into cos theta. If we convert into, if you multiply this term by 2, so that will provide 2 sin theta cos theta. So that's why we had multiplied this term by 2, and similarly we had divided this term by 2. So now we have a value minus 2 times Vm Im sin theta cos theta divided by 2, and this term 2 times sin theta cos theta can be converted into sin 2 theta. So now finally we have minus Vm Im into sin 2 theta by 2. So this is the instantaneous power for purely inductive circuit. And now if we derive the average power, and for that we will integrate that equation of power, and we will divide that integrated term by its base length. And for that we had integrated this term in range of 0 to 2 pi, and as range is 0 to 2 pi, we had divided this term by 2 pi. Let's start the integration. First of all, this Vm Im divided by 2 and this 2 pi are constant, so we can put it over here as a minus Vm Im divided by 4 pi. Now we have a sine 2 omega t term. If we integrate this term, so that will provide cos 2 omega t term with minus, and here in omega t we have a multiplication, in multiplication we have a 2, so that is going to be in division, and that's why we have this term by integration. And if we put this range over here 0 to 2 pi, and if we put this value in this given equation, so that will provide in bracket we have a cos 4 pi, so that is over here, and second range that is 0, so now second term is a cos 0, and value of cos 4 pi that is 1, and value of cos 0 that is again 1, so this 1 minus 1 will be 0. That's why average power for this given circuit is going to be 0 as mentioned over here. So this was a purely inductive circuit. So thank you for watching this video. Stay tuned with me.